online, and make sure you post on Discord to the fact that other people are also interacting. So today's agenda is very, very different. And I think you'll see this. We will do this every week along the class, where Tuesday we focused on a problem, and on Thursdays we will always have more of a technical content and starting to build your capacity to be thinking about different technical disciplines. And I think, we'll cover everything from soft robotics to optics, to a lot of mechanics, mechanical design, a little bit of fluidics and microfluidics in the context of diagnostics. So always we start with optics. It's kind of at the heart of a lot of solutions. But often enough, we don't get a chance to build and design optical instruments. And so today we have a very special person. We're going to cover a range of Frugal optics. And the first sets of labs will also be in that space. And then just before we start, just a raise of hands of how many of you have had even a small amount of experience in designing an optical instrument, where you felt that, oh, I contributed in designing. So not so much, right? So it can be optics. And again, this is also why we start with optics, because it's a huge space for a lot of people to explore. So Benedict, if you want to share your screen, I'll just do a quick introduction. Benedict is a very good friend from years now. We've been working together on a lot of different things. I remember when we started the class, Benedict was also physically here, but now far away. He's based in Jena in Germany, and is one of the inventors of a modular optics design kit, which we'll talk a little bit about. And I think eventually I have one of the kits here too. So in the lab session, you'll actually also get a chance to use it. And I think one of the key course threads to take in from this lecture and then the material that is about to become available to all of you is optics is a very large space. It has history that's more than 400, 500 years old. And what's valuable is often there is a lot of stuff that you can learn by just primarily books, and the other one you can learn by building and tinkering. So we'll make a lot of resources available to people who want to at least get some of the basics of optics out of the way. But the key focus will really be is about your hands-on experience. So learn by play. And again, then you start filling in the gaps. And for some of you, you might end up choosing that the solutions that you build have optical instruments at the heart of it. And even if that doesn't, it's still very important for you to essentially tinker with this space, because almost everything that we're doing has an optical component and it's a massive space that really hasn't actually been explored. And of course, microscopy is one. Okay, so with that introduction, Benedict, I'm going to pass to you. And then thank you again for joining on odd times and odd days, but I'm so happy that it actually worked.
Yes, yeah, I'm also well, very, very thankful that I can again participate. Thanks a lot, Manu. And yeah, so I just put together some slides. I think I'll pretty much also repeat what I've talked about last year, but there's been so much new stuff that I wanted to talk about, so that I think I have a slide deck of like 150 slides now. I'll definitely not go through all of them, but just invite you to maybe get curious about optics in general. And if you want to learn more about it, I'm very happy to also chat about it afterwards during the weeks, months, because I think optics and especially microscopy is a very important tool, not only because we are from the optics valley in Jena, but I think it's also one of the connecting technologies. Nevertheless, first of all,
Yeah,
I would like
just as a Benedict, I forgot to mention this. So I mentioned Jena. Benedict just mentioned Jena. Jena is the birthplace of optics and microscopy. That's where Zeiss. That's where Carl Zeiss and Abe who wrote down the fundamental equation of optical resolution, is literally right next door to where Benedict actually lives. So, I mean, of
Yes.
course, this happened under 200 years ago, but it's a little bit, it's not such an accident that people like Benedict are actually in Jena.
Oh, exactly. It's a very nice place to be. So swing by if you want to. Cool. Yeah, so I'll just go through major motivation about what we do. So most of the stuff we do is open science, open source. And the fact why we do that and why it's important is, of course, I mean, when we do stuff and talk about it, the fact that you don't talk about it openly until you publish it is really bad, because then nobody can participate in the innovation process. So that's something we try to change. And so in every slot, essentially, so when we have an idea, maybe the experiments, we kind of share the ideas and also the data with the people, so that there may be new influences coming inside, and then maybe we have a better understanding of what we're doing there. So most of the stuff that you see here is somewhere scattered along GitHub. So you can find the links either in the presentation or just over my link. So you usually find anything like building instructions or maybe some preliminary data, so that people can already build the stuff even before it's published. So that's also one thing I'll show you. That's called Espresso Scope. And
I just, Benedict, 1 second. How many of you have used GitHub here? Okay, so almost everybody has. So right after this, we will post some GitHub repositories for a few optics projects. We use GitHub both literally not just as a final end product, but literally as an open lab notebook. And so I think for many people, if people are comfortable, many of the projects that you're building, we'll just use GitHub as your website, as your key kind of a team building tool. And right after this lecture, before the lab, you should all poke around and see the sets of libraries that we'll just share. Yeah, go ahead, Benedict.
Sure. And then maybe just also a motivation why open source is really cool outside maybe academia is, I think everybody of you know 3D printing. And it only became big in the 2012 because there was a patent running out by a big company. And then the open source communities essentially took over and created all these fancy printers. And I'm actually right now not in Jena, I'm in a Fab Lab. It's also a big community itself. And they have tons of open source printers just behind me. And so we have to bring that to optics, obviously. And I think Manu is especially also very pushing this forward, and we are also doing the same. Yeah, optics. So where do you see optics in your everyday life? I think once you open your eyes, well, that's pretty obvious. There's already optics involved.
That's a funny joke.
Yes. I mean, light itself, candles, and of course also very interesting, because the reason why I'm here is about quantum effects. And so these little butterflies, they have quantum effects kind of on their wings with these surfaces where you then, well, in a way, trap photons. But of course also what I just said with the eyes, it's actually pretty bad lens that's involved there, but our brain is just so good that you can correct for all kinds of weird artifacts. And then also what's interesting, I think this is the first painting of somebody who was wearing glasses. So it's actually not, they're pretty new. I mean, maybe 600 something years old. So that people can actually also correct for well, illnesses and stuff like that. Then you of course have light at night. Here it's pretty dark already, so that's very good that we can now actually read and also communicate, because I mean the whole telecommunication is based on light. So the reason that you can see me now in India or in Africa or maybe even in America is that there's light being transported through very, very thin cables that are so efficient that you can just see me in, well, real time, which is insane. Then I think everybody nowadays has a cell phone. There's tons of photonics inside, camera, obviously, but also the displays. And also, I think most of the Apples, they have little projectors in their fronts where they actually scan you in 3D to make sure that it's you and not somebody else. Industry, that's also a big thing, where you, for example, can also do welding with lasers and even construct whole blades for turbines. So if there's something broken, for example, well, sometimes there are birds flying in that. So usually you throw it away, but with lasers, you can actually then repair it while they are already built. It's pretty cool. You can detect also the gravitational waves with huge interferometers. And these are just a few of these applications where you see light and maybe don't see that because it's, well, it just became so obvious. Yeah, but another application that's something where we focus on literally is microscopy.
Yeah, and then Benedict, I was just going to mention, anybody who has questions, this is really much more of a discussion because we could talk about optics, and so people should interrupt. And then the one thing that I was going to interrupt Benedict is just if you go back to that slide with the projector and the face scanning, it's worth just mulling over it for a fraction of a second to just think about how could that actually be. So it is making a depth resolution map of your face every time you turn on your phone and see. And so I'm just curious, anybody who wants to sort of comment in terms of what would you need to be able to make a pixelated depth resolution map? And I'm assuming, clearly there is a front camera, but that there is also something else. And I don't know, Benedict, was there a patent, the patent picture down below, or no? That's kind of a display, right?
Yeah, that's the brightness enhancement film. I think nowadays most
Oh,
cell phones they use.
that's actually also a really fun one to talk about. Yeah, it's just take a pause for a minute to even think about. And this is for the first lab. I'm not saying you bring your cell phones. For the first lab, people will be bringing objects and we will just be asking you to open them up and hopefully put them back together. But bring something that you don't care too much about. So maybe not your latest phone, but bring out other sets of things. But I'm just curious, is it obvious to people how something like, and again, this is the irony of what we take for granted. There is an incredible, immense technology that you could potentially use for many different ways, and something that you're literally carrying in. But sometimes it's not so obvious how many of these things are implemented. So anybody online, anybody wants to comment? How might a face scanner actually work?
Could you do something like
Just 1 second. Yeah, go ahead.
There's like a salt and pepper filter on it.
So that's some kind of a point cloud. So they're just showing that this measurement is actually as good as the face itself, but it's made independently. Yeah.
I was gonna say.
And again, it's not about right and wrong answers. It's about just thinking and pausing for a minute. I just want you to pause every time you look at something. Pause to say how it works. Yeah.
A bunch of tiny LiDAR sensors.
Uh-huh.
It sends out.
Yeah.
Light
Can you say your name one more
Oh,
time?
Henry. My name's Henry.
Yeah, so Henry just mentioned and brought up LiDAR, this idea of tiny little LiDARs that might actually be detecting distance. Was there a comment online from anyone else wants to just I see Pawan's hand is up. Go ahead, Pawan.
Yeah. So I was thinking, imagine like patterned input and patterned output, in the sense that if you put like a bunch of linear dots, like just like a checkerboard, and then you see that the checkerboard is not uniformly spaced, to like sort of unwarp the spacing, or even more fancy things, because you know that the face has some features more importantly, and you can sort of put at patterns and see how the pattern is distorted and sort of get back. So it'll be a 2D camera. You don't even need a 3D camera in principle. But because you're patterning your light projection, and therefore you know how it's distorted in some sense.
Yeah, so and again, what's fun is all of you came up with completely different sets of ideas that you could implement something like that. And then what is implemented in the sets of mass scale is always just driven by the level of performance you need, but also the cost. And the LiDARs, for example, on all the cars that you've been seeing that drive around you, they do make a 3D point cloud projection, all using a single scanning beam, for example. Okay, Benedict, back to you. I think all I want to do is just make sure that once a while we pause and then folks can think. And, as an exercise, go back and see if you can actually read enough about how that's done on your phones. And then if you find a good enough explanation, try writing that explanation up and post that on Discord. And, sometimes it's not the same as trying to figure this out for yourself is much more fun than just finding somebody else's article about it. Yeah. Okay, back to you, Benedict.
Sure. Yeah, and once you're done with knowing how the working principle is, try to replicate that in the lab and then compare the price of the components versus what's in the phone. So I think these elements, they are worth like $5 to $10 or something. And if you were to replicate that with like the typical optics equipment, that's maybe in the 1,000 range. So it's really insane what they can put into like these little sensors, and also what's the price range. So it's like the phone industry is just insane. But it's good because then we can just outsource all the different, or like we can source all these parts for science. So that's good because they're highly reproducible and also very well optimized. So that's good.
And then this notion of knowing what people have built before is very important, because if you're going to build on literally hundreds of thousands of hours and people's engineering to then come up with something else, you don't need to design from scratch. But if you don't know what is the little toolbox of what is already available, then you're starting from scratch. That takes forever. And this is kind of an advantage that Benedict, many of us that work in cost-effective solutions, is having deep knowledge of what people have done before you, and especially at industrial scale, which is super exciting. I mean, this comment that Benedict made about you'll see how when we just have one-off components, then whatever you build still can't be manufactured. But if you're going to build and design something from parts that are already manufactured for something else, like DVD players have tons of optics in it that both Benedict, many other people, we rip it apart to get, because it just, people have already figured it out. It's already manufactured at scale. And I think this is also why consumer electronics is an important space to think about, just in general, for what we're going to try to do in the class. Okay.
Sure. Cool. So just slides sweep through the applications, which is now microscopy, and just to motivate why microscopy is needed. So here you see a small variety of different viruses. So maybe you can identify some of them. So just picking two that are very, very deadly globally. So HIV, well, it took some data from 2020. I think it's still rising. SARS-CoV is maybe not that high anymore, but it's just two causes for disease where we need tools to identify them, right? So we can do that with molecular diagnostics, but it would be nice to also see them. Unfortunately, we cannot really see them with the tools we have at hand right now, but that would be our goal. And to do that, we have to develop the tools. However, the problem is that in most cases, when you see a paper and you see, well, maybe even a figure like this here, it's really hard to really replicate it because, well, in a way, it's a black box. And so what we try to do with Frugal tools, and maybe also to simplify them, is bring the people who use them and those who develop them a little bit more closer together, so that you have really multidisciplinary tools. And I think microscopy is a really nice tool because then, well, that's the bridge between the different disciplines. Nevertheless, I think we have to at least learn the few basic principles to understand, for example, how the DVD players work and then source the parts. It's just a very brief walkthrough. So what's light? I think maybe many of you know it's waves, transport of energy. And so pretty much like when you throw a stone into water, it's just emitting waves. So there's an oscillator and sending out waves from here. And so it's over time oscillating. And so you can describe light as a wave with the wave function. And so one solution of the wave function is essentially, well, a simple sinusoidal. And the sinusoidal has different properties, and the properties are then encapsulated here in this formula. So you have an amplitude, you have a phase, you have a constant phase offset, and then maybe also an offset of the whole thing. And these different terms here that identify basically all the different principles in optics. And so, for example, the frequency here, so part of the phase term here, like how fast it oscillates, gives you the color, and also well, in a way, how much energy you can transfer. And so blue light means like shorter wavelengths, more red light means longer wavelengths. And so that's, well, then depicted here in the spectrum. So what human can see somewhere between UV and near infrared, which is 400 to 700 nanometers somehow. And then you have also the ability to eventually shift the phase. So if the sinusoidal wave is essentially just traveling in free space, it may be altered by some medium. So then it's not free space or not vacuum. So for example, if you have a cell, there's waves going through the cell, so they are getting retarded. It means that they get an additional phase upshift because some part of the light travels slower compared to the one that is not going through the cell. So you may see a phase difference. So then you have like still the same wavelengths, but they just have a difference by means of high to high and low to low. And this you can then also
just Benedict, a quick comment on that. So when you normally do microscopy or even photography, the first thing you see is you start seeing colors. And a lot of times this would be what a lot of microscopy will all be doing is transmission microscopy, where light is passing through that object. And now lots of colors will get absorbed to begin with, and that'll start giving you the first layer of features. But what Benedict was also talking about is that there is another kind of microscopy that you can build on top of transmission, which is phase, in which technically it was not the color and the light was not even absorbed, but it was just slowed down a little bit by one piece as compared to the other. And this led to actually a Nobel Prize in how people figured out how to use this phase as a way to also build contrast. So classically, you will see when we will build the class of microscopes, some of them will not have this phase feature, and then we will add the phase feature, and then you'll suddenly see a massive number of things that were not visible before will become visible. So it's a very subtle way of exploiting light to arrive at a feature. And it's not so intuitive because the way it's implemented and how you detect it through interferometer is what leads to this kind of a feature. Back to you, Benedict.
Sure. Yeah, exactly. And so that's a very good bridge to the point here now. So this interferometer is essentially a way to visualize the phase. Because usually we cannot see the phase. Light is traveling so fast or like moving so fast that the oscillation cannot be detected by our eye. So we always detect an average over time. But when you have a coherent light source, that means like you have phases, they are emitted by the light source all at once at the same frequency, at the same time, at the same phase, then you can eventually split them. And then you have one arm where it moves here, one arm it moves there. And then you can bring them to interference to detect whether they are in phase or out of phase. So these interferometers, they are, for example, used for well, detecting gravitational waves. It's a huge thing, like several kilometers long, to see that the tiniest motion between one arm to the other. So then you can see that there's a slight difference between the phases, and this you can detect. And also, I think one of the biggest or like largest interferometers is created between the Earth and the Moon. So there's a tiny little mirror, or I think nowadays many different mirrors on the Moon, and then you can measure the distance between the Earth and the Moon by just measuring the difference of the phase, or like how much phase difference you have.
So Benedict, there's a quick question, and this is the moon mirror is kind of funny because now I want to look through on the telescope and see if I can find a mirror. Go ahead. There is a question.
Yes.
And can you also introduce yourself?
Yes. I have a question about the interferometer. So I just wanted to understand it. So there's two light sources, and so they're shooting the light, and then the mirrors are reflecting it back. And how do you determine, like, at what point they should intersect to determine, like, the phase difference?
Benedict, could you hear it?
I guess partially. So I don't know. I have my cell phone also here. I don't know, whoever is So I have a second camera because I prepared with the interferometer. Can you see?
Oh yeah, let me get you into the demo mode. What is the name of your
It's also Benedict.
also Benedict? I'm searching. Give me a second. That is important to find. Oh, who saw it? Where? One more up. Where? That one. Oh, yes. Okay, Benedict, I am spotlighting it.
Okay, cool.
Add spotlight. Is that what just happened? Now it's there. And then you can also unshare your screen.
Sure.
Yeah. And again, this is valuable because we will do some demos and lab around this. And then just kind of one way of thinking about this idea is you're using light to detect phase difference in light. Because phase difference is relative to one wavelength. And so you are letting them somehow talk to each other. And how do you let them talk to each other? They literally come together. And that's kind of the word interference is essentially two things interfering each other. Because the oscillations are so fast, we don't even have a detector to detect it. But we're exploiting this principle that we can use one light beam to detect another light beam. That's why you see these two arms. Yeah, go ahead, Benedict.
Sorry, yes. So exactly. So essentially you don't have two light sources, you have one. And so here we use a laser. So it's a typical green laser pointer you would see maybe I don't know, on a concert or something. And so then you split it. And so that means you start here with T equals 0. So it's same, they oscillate same time, they just oscillate the waves, and usually, well, there's multiple waves, but then you split them half. So there's a mirror that is 45 degrees and 50% goes that way and 50% goes that way. And then that means there's another mirror here. You see here that's a 100% mirror, and there's yet another 100% mirror. So that means you copy the one beam here, then there's another copy here, and then they are getting reflected back, and then they interfere on the screen. So that means you compare two different beams at two different time points. And I must admit, this is fairly poor interferometer because the mirrors are not very flat. So that what you see here, this shivering X is basically one wave plus the other. So when I'm blocking one path, the pattern is gone. And when I'm moving it back in, that means this is then the wave 1 plus the wave 2 at two different time points. And so that's basically the interference you see. So the black means they cancel out, and the bright means they just enhance. And that's constructive destructive interference, and that's basically the whole principle.
And it's the most sensitive way that we have invented as humans on measuring distances. Because frequency can be converted and thought of as distance, and even a very subtle change. And that's why LIGO uses the world's largest interferometer, because the space-time warping for any gravitational wave is still very, very small. So if you really want, for example, I mean, the instrument is actually very low cost to make, but if you're really after measuring very subtle changes in distances, this is a technique that you would use. But it's also just a fun technique because it has history, it's also building interferometers is just fun because you learn all aspects of optics in kind of one go.
Exactly. And so just imagine.
And there was one more question. Yeah,
So
go ahead.
the mirrors have to be equidistant to the splitter, right?
Mhm.
So how important is it, like, how hard is it to get it exactly?
Yeah. And because it's a wave, it's only the periodicity that matters. So what you're after is the periodic length is what we're trying to deal with. And I think one of the other things to think about is you can use your interferometer to calibrate your mirrors. because you say, hey, I'm seeing a dark pattern here. Let me move one mirror until a point that it will be the n multiple of lambda. And you're not measuring total distance with that tool.
Exactly.
And there is a trick that once you know, you can also measure absolute distances.
Exactly. And so what you see here is like the periodicity of what Manu was just talking about. So imagine you move one of the mirrors just in one direction. So that means you move one sinusoidal over one that's stationary. And so what you end up, the interference is essentially the sum of the two. And whenever you have a low, that means deconstructive interference, and the other one is constructive interference. And so in an ideal world, we just have a laser source that has essentially just a single peak in the wavelength spectrum, like in that case, it would be 532 nanometers, then you see this perfect sinusoidal interference pattern as long as you move the mirror back and forth. However, we don't live in a perfect world, so you always have a spectrum where you have, for example, small portions of slightly longer wavelengths and slightly shorter wavelengths. And so that means in the end, you can measure distances with colors. I think I'm also coming to that point. I'm just going through, so imagine you have now a perfect green light source, and then this is essentially the interference when you move the mirror. So there's the peak in the center, and then you have slightly shifted interference pattern for the red and the blue. And when you interfere, let them fully interfere, you see that there's a perfect match for all the colors, and then it's vanishing very fast. And so this periodicity is still there, but you cannot really distinguish it anymore. And so this is a perfect sensor for absolute distances, because there's only a single position where the two distances perfectly match. And if they don't perfectly match, that means they're out of sync. And so you can just control the distance and the position, and then measure the distances. So this is,
and then there's a very nice analogy of thinking this is kind of like music, in which certain beats then match perfectly, because you have completely different wavelengths, but there is a point of time, and n multiple of one wavelength is equivalent to an m multiple of another wavelength. And that's why there's only a particular distance at which they will again clash.
Exactly.
I'm not, Benedict is a great musician, but I'm assuming that in music, people use these tricks, right?
Yeah.
Right, Benedict?
Oh, yeah, sure,
Okay.
like all the time. You'd have the tuning fork, and you hear that pretty intensely. Right. And then let's move on. So we know that the moon is very far away, and then we can actually make an assumption. So if something is very far away and the pumped light, or like the oscillation, is moving very far, that means that the wave here, they come from a spherical, and the sooner you go, or the further you go out, the more straight they get. And then you can move from the ideology, or like the idea of having waves to become straight lines. And then you could talk about ray optics. And the easiest trick to visualize that is essentially a pinhole camera, or camera obscura. So you just take, I don't know, a Pringles box. I think they are pretty much available everywhere. You punch a hole in the metal plate, and then place a whiteboard on the other side, and then you see that it's actually a camera. So you see that everything that's in front of the box is now flipped, and you basically just draw the lines from one point to the other, and then you form an image. And you also get these very tiny pinhole cameras where you can then have essentially lensless imaging, which is kind of cool. One thing you also have in optics is light matter interaction. So as soon as there's light, it will interact with something, if there's something. And so the phases, they're getting altered by the material's properties. So usually you can summarize that in refractive index, for example. So light is reflecting, refracting, and diffracting. And so, the underlying principle is always the same. So you have to solve the wave equation, essentially. And so what's happening here, you have light. Let's assume it's coming from the left-hand side, and then it's interacting with the points. And the more points you have, you see, the more it scatters. So the light is going through the scattering, and then you have multiple scattering, because the scattering in advance is scattering in the preceding events. So that means light matter interaction can be really, really complex. And that's also the reason why, for example, holography or like holographical displays are really hard to deal with. And one thing you can identify that really easily is like you take a laser pointer, point that to any surface and observe what's happening if you move either your eye or the laser. So there's a very distinct pattern, which is called speckles. That's essentially, well, a million different microns and interferometers if you want. So because every point is creating its own interferometer, and then the resulting envelope is then going to your eye, and then you see the interference of many, many different scattering events, which is also used for measurements. You can also use that for very, very precise measurements of the surface roughness, for example. What you also have is
the speckles. Have you all actually observed speckles? When you point a laser pointer, it doesn't look like a smooth, right? And the point there is this is a reflection of the surface. And then the surface by itself generates a new beam. And so then you can see lots of beams. I mean, millions of beams have been generated. And there's lots of places where people are starting to use speckle patterns as a way. One application that I know, which is a very clever application of this, using scattering and speckle, was in my graduate lab at MIT. They built a new kind of a lock and key, which didn't have a lock, didn't have a key. It was an optical lock and key, but you needed to know which angle, because this is extremely sensitive to the angle. So the lock will only open if you could actually shine the light at this very particular angle. And then the key was a medium of beads with resin. And there are millions of beads, and there is no 3D printing technology that can replicate. So I can, like a normal lock and key, I can give you a key and you can go to a shop and replicate it. That's not very secure. This is an object, you can look at it as much as you want, but it has 3-dimensional positioning of 1 micron beads in a very large volume. We don't have a technology to replicate it. So it's a little bit strange to have a physical key, but not be able to replicate it. And of course, it costs 20 cents because it's glue and beads inside. And that's exactly what Benedict is showing here, because even one bead missing and the pattern is different because they are talking to each other in this multi-scatter approach.
Which makes things a bit worse if there's dust in the way and then you cannot open the door
That's
anymore.
correct.
But I think that's a different story.
It's not a practical solution.
But it's really cool. I like that. I mean, they use it, for example, to define or like to measure the roughness of the street in autonomous cars these days, so that you know, okay, a wet street, for example, scatters differently compared to a dry street, and then you can adjust the speed accordingly, which is
I didn't know. Do cars do that now?
Yeah.
You think cars have a sensor for wet and dry street?
It's coming, yes. Yeah.
I see.
They used exactly this here. So just imagine like a rough street as, or like more reflection or less reflection. You can measure that. And yeah, well, reflection, that's also one thing. Just briefly, I think everybody knows what's a mirror. So it's just basically, waves going in and going out, and there are some very interesting effects here. So you can also use mirrors as kind of lenses, or like at least for imaging. And there's a very bad example where this happened. It's in UK. So there was a skyscraper. I'm not sure whether it's still like that, but it was formed as a parabolic mirror. And so it has a focal point. And so inside the focal point, there's something, it starts melting because of course it's getting really, really hot. Yeah, just as a bad example. Absorption, well, that happened when
is that a car parked at the focal point of a building?
Yeah, so this is the real image. So yeah, and so absorption is essentially then well, light is
for a newcomer, they won't know why is that parking spot always open.
Exactly.
That is really funny.
Yeah, that's really, yeah. And so absorption is also used right now. So the camera that is visualizing me and my surrounding has little filters that absorbs essentially the wavelengths out that is not needed. So usually the pixels, they just detect whether there's light or not. So they convert photons into electrons, but it doesn't know which color. And so color filters essentially do that by abstracting the rest. And so then you can have red, green, blue pixels, and then construct natural colors by very funky calculations. So refraction.
So Benedict, just a quick comment on that. If you go back to,
Sure.
so this is, if you go back to that slide, so that's called the Bayes pattern. You see, this is all on your phones, on your screens. If you put your cell phone screen on a microscope, you will see certain class of a filter pattern. And then, do you see something unusual about that? You see red, green, and blue, but it's a checker pattern. You only have 3 filters. Do you see that something is overrepresented there? What color is overrepresented in that green?
Isn't it because visually we see green more?
Yeah, I actually don't know the
I
answer.
think I looked this up.
Yeah.
It's because
Yeah.
humans, I mean, we're animals and have to see green more.
Yeah.
And I think to replicate our vision, they have to put more green.
Yeah. But
this might be an aesthetic.
and also there is a symmetry. I mean, mathematically, you can try coming up with these classes of things. You want these point patterns to have certain classes of symmetries. And then you can try designing your own pattern. And then, Benedict, I do know that there are other patterns also that are commercially used other than just the Bayes pattern.
Yeah, I think so. The reason I guess I'm not 100% certain is it's so the spectrum of the sun has a peak in the green, and that's also reflected by the chlorophyll, like the process, like how to how plants essentially work. And so I think that's also the reason why there's a peak in the green vision of maybe animals and human.
We evolved based on the but
that's
more of your camera pixels are dedicated to one color.
Yeah, so I think you also have sometimes yellow, so they say that you can visualize better contrast, but I'm not sure. I think it's also a bit marketing.
But there is a fabrication process that arranges filters in this beautiful manner, and suddenly you can say, oh, that's a part I could use. I mean, this just implies it's not trivial to make something like this, but this thing is made by the millions. Because every little thing has this Bayes pattern on it. So then you can ask yourself, wait a second, if I want to actually use something that has these color absorption things, but at a very small, because these things match the pixel size. So the pixel size could be 1 micron, 2 micron. So this is very, very small. And this is that's why we don't perceive something like that. You really see the resolution of color cameras technically is much lower than monochromatic. But now because these are small enough that it start to really match.
And then also, I think nowadays the pixels are so small that the wave nature of the light is also playing there. And then you also have not only the color filters, but sometimes even lenses on top so that you focus the light on these little sensors so that you have higher efficiency. So it's really worth just Googling electron microscopy images of CMOS camera sensor. It's really
what's the highest megapixel camera on cell phones now?
I think 80 to 100 megapixels from Samsung.
100 megapixel?
So they have a pixel that's in the range of the wavelengths of the light it's detecting. So then that's adding whole new statistics on the noise level, because then you measure outside of Poisson sometimes. It's really interesting. Yeah, so cameras are really insane, like but how they are manufactured and no errors. It's really impressive. Right, and then talking about refraction, that's also the reason how we can image. So I think everybody has seen a lens. So I'm just putting that in front of my camera here. And so you have a ray, and then it's kind of bent at an interface. So you have, for example, air to water. And so the reason why it's then bended is that it can move much faster in a media that's less retarding the light. And then at the interface, it kind of, well, it has the effect of shrinking it, so that it slows down. And you can also visualize that with marching soldiers. So then you have, for example, street, and then this is mud or something, and then since they all have the same face, they have to bend in order to still be well next to each other, which represents the wavelength. And then you can use that, for example, for telecommunication, as I just said. So this is then total internal reflection. So if you have this interface, water to air, you can bend the angle following the Snell's law. And at one point, the array won't point out anywhere more, because then you won't be able to solve this equation anymore. And then you can reflect light essentially without any losses. So that means there's no energy really being transported here. However, that's not really possible. So there has to be some energy, which is then called evanescent field, but it's not really absorbed anywhere. So it's just, well, energy you could sense, but essentially it's a lossless energy. And so, yeah, and then also the effect of different refractive indices. For example, you can build lenses that can literally bend the light. So usually you would expect like a straight line, but here you have a gradient of refractive index. So you have just water, and you pull over some sugar, and sugar has a different, or like sugarish water has a different refractive index than non-sugar water. And so then you can bend the light, because the lower you go, the higher the sugar concentration, and then the angle will increase. And then usually, or back in the times, you use this principle to
So
measure.
Benedict, just in that photograph on the right, a slide before, that has a gradient lens, right?
You mean the one in the aquarium?
Yeah.
It's just water with sugar. So
No, but the sugar concentration, is that constant or is varying along
no. You haven't mixed it properly. So then you, like in the lower levels, you have higher sugar concentration, and then
Yeah, so that's called a gradient lens.
Yeah.
So effectively, and it's, you can see normally you draw straight lines, but in constant refractive index materials. But now the material itself has its refractive index continuously changing. And hence you can actually make a curved line. Normally in optics, you won't draw something that's curved, but it's curved effectively because at that resolution, molecularly, it's changing. And I think this is also just because there is a density fluctuation when you add something. So these patterns will naturally form. So then you can think about, oh, I have a trick here of making new classes of lenses, which are great. These are called grin lenses that don't have a constant gradient. But you can think of, sugar might not be a very practical way. Although now I'm looking at this refractive index change for sugar, it seems sufficient enough that grin lenses could actually be made this way.
Yeah, no, I think
Not totally crazy for when you're thinking of a macroscopic, because again, a huge issue is the manufacturing of materials in that space. And so this is why in the old times, for example, when the mirrors were being talked about, when we didn't have very good polishing techniques, mercury would be used, liquid mercury, because it's using the law of physics that liquid mercury, because of surface tension, is atomically smooth. So there's no polishing. So some still very old telescopes actually use masses of mercury that are spun. And again, this is just about this idea of, can you exploit the physics to be able to create your optical component itself, which is otherwise polishing mirrors is extremely expensive.
Yeah, especially for those tools that are fabricating our chips. So maybe you remember Lars from Zeiss, and he always talks about the mirrors that are imaging the semiconductors. They are so flat that on the surface of Germany, you could not spot anything that's bigger than a human hair. So that's, just imagine like how, sorry, not human hair, like a human. Like you can spot like a tiny imperfection of the mirror that's being polished by huge or like tiny scales. So it's really impressive what they can do there.
Benedict, there's a question from Henry.
No, I think someone in the chat.
Oh, I see. Henry is pointing out that somebody in the chat has a question. I will open up the chat for a second. Was
If
there
you
a
can-
question?
The person asked whether he or she can ask the question. So go ahead.
Yes. Go ahead.
Okay, so I have a question on the energy thing. You said the energy actually doesn't go away. The energy is constant while passing to the another medium. So if the velocity is lower of the light, so where did that kinetic energy go?
So you mean the evanescent field?
Yeah, I think he's
Yeah,
just
yeah.
asking about the loss in an optical fiber. I mean, effectively, there are other places where there is a loss.
So yeah, in a well, again, perfect world you would not have a loss. In perfect worlds you unfortunately have a loss. But it's essentially a solution of the wave equation. So you have I mean you cannot have an abrupt change. So if you just calculate this scenario, then you see that there's an exponential decay of the energy that's kind of lurking in the infinity space outside the interface. So I think this is not really solving the question there, like the question, but
So can we say that the photons are actually losing energy, right?
Yeah. I mean, one way of thinking about it is all optical fibers still have a loss. And this is also why we have boosters and amplifiers in the ocean, for example. So beyond a certain amount of time, when they lay out these cables, there is an optical amplifier. And I don't know how they power it, because they then have to power it under the sea. But over certain distances of times, for very long distances, you essentially put amplifiers to boost up the signal. But I'm assuming most of the energy loss, Benedict, is in the evanescent field itself, right? Not in the absorption, or not just in the transport in the fiber.
I must admit, I don't know. I think that the problem is rather that you get out of sync. So the longer the fibers are, and again, you're not having a perfectly narrow bandwidth laser source. So that means the beam is being stretched. So you send a pulse, and since you don't have only one wavelength, every beam has a certain delay for every wavelength. And so if you travel, let's say 100 kilometers, they will arrive at different so that means you need to well boost for sure, but then you also need to resynchronize them so that they are in phase again, because you have a very well the material has not only a refractive index but also well, like the color induced
chromatic. Yeah,
exactly. Yeah. And so that's yet another problem why you, for example, have also the effect that you have rainbows at very cheap lenses, because you would need to correct for it for different wavelengths.
So the chromatic context is that when you say there is a refractive index, you're saying that for a particular wavelength. But now, if you have a color picture that you're sending through a lens, all wavelengths have different, so they bend slightly differently. And that's why you actually see, so many of the optics that you'll play with will have a little bit of this rainbow effect, where the images are forming a little offset. And that's the classic chromatic aberration.
Yeah, you may see that here a little bit. So this is, I think, the cheapest lens you can form, maybe just the foil, water, and then the sun that's being focused on some black paper to ignite fire. And you see like this rainbow effect. Well, I think there are multiple effects here, but this rim here is essentially also a chromatic aberration. Yeah, and so this brings me to the fact, well, how lenses work. So you now don't have only a straight interface, but a curved one. And so for every ray you draw, you have to essentially do Snell's law. And then if you do the integral, you come up with a focus point, which right now is not really accurate here with reality, because it's not focusing on the perfect point. Because well, you have then all kinds of aberration if you have an imperfect lens. And so unfortunately, there won't be a perfect lens at all. So you always have to construct objective lenses. So that means you have multiple lenses connected to form perfect lenses. But you can play, for example, with this very cool 3D printed lens that is filled with water. So you have these two foils, and then you can blow it up and then increase or decrease the focal length. The focal length is then essentially the distance from the lens where light that is coming from infinity focuses down to a point. So essentially, I think here is better visualized. So from the principal plane to the point that's the focal point. And so you have then.
This was obvious to everyone. The lens is two foils. I mean, just that
Oh, sorry.
it was proposed in for programmable optics because, as many of you know, eyeglasses are not accessible to a lot of people, and that's because everybody needs custom. And so this was an idea that was proposed. It's never actually taken off. A few of my friends tried starting companies in that space. The quality is not good. It's bulky, but the physics is very clever. You're just using pressure to inflate and deflate a balloon filled with oil. And so just if you want to tune your lens, you don't go to the doctor. There's a little screw that you tighten and you say, now I see better. So, I mean, theoretically, it's a really fun idea. I think a lot could be done in that space still. But it's valuable to just going back to that same idea of how do we exploit laws of physics to give you optical components for free. So similarly, ball lenses are very powerful because there is a very, it's a mathematical theorem that you can take any object and you can throw it between two plates and vibrate the two plates at a sufficiently long time, that object will erode into a sphere, a perfect sphere. And so this is how ball bearings are made. This is how every object that uses spherical balls is made. And so you don't have to be working hard. And then when you throw many stones in this grinding plate, they all average out to a single size. So there is a batch effect, but they naturally average out because if there is a big stone that's taking more weight than the small one, and then it'll wear out faster. So again, another principle of exploiting what happens naturally as a way to building an optical component. Yeah.
Why is it hard for this self-adjustable glasses to take off? Seems like it's such a straightforward thing.
It's too bulky. It's not fashionable. I actually know the history of this because of one of the friends who started the company. You know, it's the markets are flooded with secondhand glasses. And so people are wearing glasses that are not perfectly tuned to them, but they look nice. I mean, and again, going back to that social context of what we had talked about, we could ask ourselves, why did Google glasses not take off? You know, why it just, and again, I think there's some technical problems there too, because it's not a perfect, when you have pressurized chambers, the curvatures, you need two independent curvatures. And so there are limitations in these glasses also. Yeah. You don't want like your lens to burst out and yeah, so I think it's, but having said that, it's a question that many of you could think about. Still today, by numbers, a significant people don't have glasses. Yeah. Benedict.
So, yeah, sorry. I think one thing that also is worth thinking about how the technology has to be matured for printing lenses, maybe as eyewear. So,
Yeah.
because there are companies printing lenses, but very small, a lot smaller scales. But I think at one point maybe that's even possible to print optical quality lens surfaces. So it would be interesting to see when that's possible.
So what Benedict is referring to is 3D printing. Yeah. Mm-hmm. As a lab, we did a lot of work. So when Laurel was in the lab, we came up with very clever ways of using surface tension and printing together to make lenses. And so I think that field is really in its infancy, but it's not totally crazy to think about that next time or 10 years from now, you go to your lens maker that they just print out your glasses. And you get to customize every possible thing about it. But yeah. The moment optical components become 3D printable, you can see an incredible explosion in integrated design. Because, you know, then you can make any arbitrarily, and then there is no assembly, because the assembly cost is what makes. So we will talk about this in the lens, but as for microscope lenses, the cost sometimes is not even in the objective, all the lenses, but how precisely they have to be aligned to give you, so a regular, really high expensive microscope objective can have 20, 25 components, and they all are incredible tolerances, and every piece has to be in the same position every time. And so sometimes when we think about cost, it's not the material cost, it's the assembly cost. And so for a lot of things that you'll be thinking about, because you want to reduce the cost, you might come up with ways making optical lenses which have integration.
Yeah. Yeah, I think that's very much
Right there.
So this is a pattern from some objective lens for a microscope that has a higher magnification, and you see, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9 optical lens elements, and so they all have to be in the perfect shape. They are hand polished and hand put together, and then only if this is true, then they form these images. And so now imagine this is roughly the size of your thumb. And there are these lenses with a diameter of roughly 0.5 meter to illuminate the wafers to produce the chips. And they have the same optical quality, but just on like, I don't know, 50 centimeters lens radius. So this is really insane. Nevertheless, what's also insane is like on the left-hand side, the camera's lenses in your cell phone. So they have the same optical quality, and what's bizarre is like they're looking here. So these are like just the spherical lenses, what we have just seen. So just an ordinary curvature, and they are almost free form. So it's an aspheric lens in order to compensate all kinds of weird artifacts, because they are now not glass necessarily, but maybe injection molded, and then squeezed together to something that's less than 2 to 3 millimeters wide to form the images within a very compact design. And then you also have these voice call actuators, for example, that is then doing the focusing, the image stabilization, and all in a very, very compact housing. So it's really incredible.
I don't know if it's obvious. The little lens there is actually moving up and down.
Yeah.
So that's kind of when your camera tries to focus, and you can actually see, and we'll use voice coils for all kinds of things. It's a really fantastic. You can also see the magnetic copper wire right there. And that's what's making, so now not only is this a lens assembly, but it's an actuated lens assembly. And then the joke, of course, in the cell phone industry has always been is, why is there a bump? All cell phones have a bump. That's to accommodate, because we're now talking about, I mean, just look at this thickness. You're accommodating the sensor, all the optics, everything in the context of just this thickness.
Yeah.
And one day there will be no bump.
All holographic, yeah. So there was also an area
meta
of
surfaces.
Yeah, exactly.
Yeah.
And one thing I think what you then should maybe look up for the next lab is get out your optical pickup units from the old CD, DVD, whatever drives, because they have all tons of optical elements in there. So so they look like this here. They have sometimes 3 beams that are measuring the track distances. So to focus the beam on the CD, and I don't know who of you still know what a CD or DVD is. It's an optical disc where you have
Everybody
the information
knows, right?
Great.
Yeah. Yes.
In binary information in little tracks. So you burn the zeros and ones in the silver foil, and depending on what kind of disk you have, you squeeze the information in smaller or bigger amounts, and then you have to read it out optically. And what you see here is, well, you use almost UV light, very, very accurate lens, and then you can go down to information width in the range of 250 nanometers. So only because you can squeeze so much information on such a small area means that you can have Blu-rays with 50 gigabytes of data, and sometimes even more if they are multi-layered. And then skipping all the stuff here. So this year is a bit that you can have CDs with only 700 megabytes and Blu-ray players with almost 50 gigabytes. That's all coming down to this formula here. That's stated by Abe. So I skipped most of the parts because it's, I think, almost going to the end already. But nevertheless,
and then one thing, Benedict, what I'm thinking a little bit about is that there is so much content that it might be that some of the content will continue on the Tuesday, because I think this interactive format is so much more fun to have people conversations. And then what might be very useful is because then on Friday, people would have seen the UC2 and a couple of other optical components. So then it might be useful. We can talk a little bit about on sometime next week for you to only present and very specifically talk about UC2. I think it might be a better way of structuring it because then it has a more physical format to it. But we can figure out the timing.
Yeah, sure. Right.
Yeah, so maybe one thing you should think about is let's do 10 more minutes as a closure, or maybe a 5 more minutes on the Abe and the resolution side of the story. And then I'll send you some messages offline in terms of the UC2 demo, because I have the anglerfish demo that I was thinking of planning for this Friday, which is tomorrow.
Right. Yeah, so let me just quickly go through. So this formula here essentially says, okay, the lambda's giving our wavelength, so the color using for imaging. And this bizarre term 2n sinusoidal of alpha is essentially the ability of the lens to collect the light that is transmitting the information. So that means like if you have a very large lens, there's the ability to collect more information. If you have a small lens, then there's not so much information going through, and that's basically signal processing knowledge here. And so that means you can have small wavelengths, and then the D is giving us the smallest possible resolution, or like the distance we can measure. And small, so it means large lens and small wavelengths gives us the resolution limit. And so that means we can roughly measure by half the wavelengths of our microscope. That's roughly 200 nanometers. And that's also what the Blu-ray players are doing. And you can observe that without so much of theoretical background. So if you stare at the night and you see some stars, then essentially every star has the same size. And that's a bit weird because I think there are some bigger stars, but that's only because they are brighter. Because that means our eye has a certain ability to detect or like to capture the light, because our iris is having a certain diameter, that all the information that may point to a smaller spot of the star that's maybe depicting to smaller star, or maybe further away, it's just throwing away. So that means like on the retina, every star has the same width or like the same diameter. And that's also the problem in microscopy. For example, here there are some viruses in different colors, and they look all the same size, but only because they may be smaller, maybe 50 nanometers or 100 or 200, but below the upper resolution limit, all the stars have the same diameter. And there are tricks to resolve it better. So for example, here it's a very funky video where you have the Eiffel Tower, and then you just use the schema to let the different point sources blink over time, and then you can resolve better because you know, okay, that's the centroid of my emitter, and then I draw here and there and there. And with these kind of tools, you can then resolve a lot better. And you have a whole toolbox of different things you can use in microscopy. For example, fluorescence is one thing where you then can, for example, label your specimen with certain fluorescence proteins or also synthetic dyes. And then you only label the structure you want to see, illuminate that, for example, with a laser, and then you can distinguish between different compartments of the cell. And what we're trying to do, to just give you a very slight glimpse, is essentially making all these tools that are usually very, very expensive, much more approachable. So these are usually the tools you use, and those are the tools you can replace them with. So there's always something that's much cheaper. For example, cell phone cameras are perfect lenses for your microscope. It costs literally nothing. And then with these tools, we can then maybe at one point replace the long history of different microscopes with newer ones, and make these bulky microscopes a lot more cheap. And so one thing I definitely want to show you is like the easiest way to construct a microscope. I think everybody maybe have seen those, or maybe even the Foldscope, and they're based on the same principle. So you can take, for example, a ball lens, or maybe an objective from a proper microscope, or you just take the cell phone lens from an old cell phone and use this kind of retrofit mechanism. So that means you have one lens right in front of the other, and so they essentially compensate that, each other. So that means you have a point that's brought to infinity, and then the infinity part is brought to a point. And so here in the ray diagram, it looks like, okay, there's a point, image of the point, another point here, also mapped onto the point. So it looks like you have a, well, here, -1 magnification, which doesn't sound much, but since every pixel here, as Manus said, is in the range of 1 to 2 micrometer, means that the whole field of view here is maybe just 1 or 2 millimeter, and then brought to the whole screen because the cell phone is then doing the visualization of the whole sensor that's 2 millimeters on the size of, for example, 10 centimeters. You get an increase of
magnification. The subtle thing to understand here is that the reverse lens is literally the mirror of the lens that's already on your phone. And because they are being manufactured at large scale, if you just take two optical components and flip them around, you naturally get a microscope. So it's exploiting this idea that the lens on the right is being manufactured and made at large scale, but for macroscopic imaging, but it's taking a macroscopic scene and converting it into a microscopic because the sensor itself is so small. So whatever optical transform it did, if you could just reverse it, you would actually get a microscope, and which is what that, so that object is literally the mirror of the other object.
Exactly.
And I think, yeah, maybe one thread is, I think I have some of the M12 lenses that we'll bring out in the lab, but it might also be fun, Benedict, we should find a good source for large number of these cell phone lenses also. That's been kind of a, I want to go beyond those M12 lenses.
Yeah.
I mean, you don't want to break your iPhone to then find another and then put it on, but these are made and these are OEM manufactured. But it's a very clever trick. And actually the trick was first discovered in photography because people wanted to do macro photography, but you couldn't buy a macro lens because they're way too expensive. And so people started taking lenses and mounting them completely upside down. Like it's the same joke that you use a binocular the other way around. And that's how people actually discovered. And then, of course, it became a big thing. Yeah.
Exactly. Yeah. And you can also do that without a cell phone. So that's something that's the whole point about espresso scope or anglerfish. I don't know how you may call that. So it's essentially a small microcontroller that has one of these very old cell phone lenses. But if you then just either unscrew it a little bit or just use the same phone lens and reverse it, then you create a microscope, and you can magnify down to the point of 2 micrometer to 3 micrometer resolution for less than €10. So it's a very fun experiment to just try out. And I'm not so sure. So maybe just giving some. So how much time do we still have?
Yeah, I think I'm thinking that we should pause at this point and then pick up the next week, because I'm realizing that there is still so much content, but without this background, it's hard for people to actually appreciate. So maybe I'll ping you whether either next Tuesday or Thursday might actually be open. And, I think one of the big threads would be is because for the espresso scope, I was thinking this time, everybody collectively actually will try printing a few also, because, I think, yeah, and it'll be a fun test case for the manuscript too, because then
Just
we can get,
upload it.
yeah, we can give people the instructions and see how much kind of independently they can all put the entire thing together in some way. So I don't know, what does your availability look like on Tuesday or Thursday next week?
I think Tuesday is a bit too early, so the next Thursday would also be good again.
Yeah, Thursday is good because I'm anyway switching back and forth between the technical bits and other, and I think, I can cover a lot of the other tools, but UC2 would really be fun for you to cover, because you can also talk a little bit about, do that as a case study for a project rather than information, because sometimes history is also very important for people to understand, how projects come about. And again,
Perfect.
this
Yeah,
class is not just about the objects, but the people behind those objects and why they create what they create.
and maybe, well, I wouldn't say as a homework, but just maybe a source of inspiration. So the Matchbox scope, which is now called Espresso scope because the ESP is the underlying device inside. There's
Espresso because of the coffee, and
Yes.
ESP is the microcontroller that we are using to make it, which is a very cheap, very powerful microcontroller.
Exactly. And so that's also maybe referring to the first initial thought, like why open source is important. So this now is available everywhere. So you can just replicate that. And it's really just like this printed part, some screws, and then you're done. So it would be a very nice thing to just try out. So you can either get it on eBay, Amazon, or something. And it's widely available, hence very reproducible. And the other thing that I wasn't going into today, as of now, just some saw the interferometer. That's this cube-based system that's called UC2. And so we also have tons of information about like how to construct these kind of things here. So it's basically holding optical elements within cubes, and then you can just combine them to arbitrarily complicated systems. So I'm just copy pasting the links here, and for everybody who's interested to get to know more about it, just feel free to look here or just ping me. I'll be available.
Yeah, and I think one thing that I was gonna do, Benedict, was the next Thursday, let's do a session primarily on UC2, because this year we have several lab spaces with lots of 3D printers. And so one of the threads would be is for people to actually choose as an assignment, because the optics assignment I was gonna assign was really around that everybody kind of tries making one new component for the UC2 library. So the UC2 idea is optics as Legos, quite literally, because these pieces snap together. And then every one of you will just choose one optical component that doesn't exist. This is also a good excuse to learn CAD. How many of you know CAD? So half the class. So I think this is very valuable, because then you can take the CAD pieces that are already there, mush mash them together. But I think let's do that. Let's do that offline. Do you want to unshare your screen for a second, Benedict?
Sure.
Yeah.
Can
Question.
Benedict share the links on the Discord as well?
We'll put that online.
Okay.
Yeah.
Yeah, I think it's also an optics sub. So then I can just look into that again.
Yeah, and I think on Discord, we will create, just like we do this for every lecture, there will be a channel. So ask, and again, this is also true for everybody online. Ask questions, post sets of ideas. If there is an optical instrument that you don't understand, just share it and say, hey, can someone explain? Before we disperse, two key things. So we'll have our first lab tomorrow. And for the first lab, one of the things that we will do, and this is also true for everybody online, when you come to class tomorrow, I'm going to ask you to bring one object that you have wanted to open and know what's inside. And you are okay opening it up. You are the one that will be opening it. You'll put it back together. It may or may not be that you can put it back together in its correct format. So it shouldn't be something that is so dear to you that your life depends on it. But it can be anything. It can be a medical device. It can be a calculator. Bring anything, but everybody to enter the lab, you must have one object. It's not about the complexity of the object. And again, some of us, we will, as a collection for stuff that you bring together, we will look at each other's things. And so, you might say, oh, this is interesting. I want to watch the disassembly. So we'll just be disassembling and then hopefully trying to also assemble them back. But it's a requirement. And I think this is also true for everybody online. This is, what I'm trying to emphasize with the first lab is remarkable technology is surrounding us, and we often don't even realize. So if I was to just open this object, I would learn a ton of things that went in making a very simple, or what we might think as a simple object, but it's not. And so I think that's kind of the principle. It doesn't the more variety of things people bring, the better it is. So it doesn't have to be just everybody brought optical things. Bring anything under the sun. And we will, if you have a tools, bring it. Otherwise, we have tools here for this assembly. We'll kind of spread out. And I think this is also just true for everybody online, is to just make sure. And if you already know what you're bringing tomorrow, just post that on Discord, because it'll be fun. If somebody is bringing, what is the oldest computer in the world? The Greeks made. You guys know what I'm talking about? The Archathon? No? Okay, now I have to show it. Okay. Whatever you bring, please post it so that we have a chance to see it. And I think, Benedict, what I'm thinking is Thursday, let's do the UC2 session. And then the next Friday, we will then end up doing UC2 plus the optics demos, maybe UC2, Foldscope, and Espresso, something like that.
Sure.
Yeah, because I'm just realizing rather than tomorrow, that'll just give me 1 week to also prepare and plan and see whether we can get some of the 3D printing going already here.
Sure, yeah. And if you have any questions, I'll be also in the Discord channel, so just ping me in today's class.
Yeah, and then I think the sets of people that I invite to the class also play a role of mentors for projects. So one of the key things is, as teams start to develop, mentors float around and they come and help based on the time availability they have, but also just driven by needs that people have. So Benedict is one of the maybe around 10-ish or so mentors that will be around. Okay, I just want to say thank you, Benedict, so much. It was a last minute notice. I know it's probably late on your end, and looks like you're not in yet. I'm curious, which Fab Lab are you in?
It's in the industry area of Germany. It's in the Ruhrgebiet. It's where the coal mines were back then.
I see.
So it's interesting because I wanted to show. So they kind of adapted our design for robots. So and what we try to bring them to
that
school.
is hilarious.
It's pretty cool.
That is.
Same factor. So it's. Yeah.
I'm trying to do I don't know how I can make that large. Oh, pin. Pin. Continue. Can you show that just one more time? So what's really funny about this and evolution of ideas, that was the UC2 design for optics. Because Benedict opened it, he shared, and somebody then built robots using that framework. And this is what's fun about sharing what you do. Oh, this is so fun. I did not actually know that.
Yeah, we try to make it compatible so that they work somehow together.
No, I mean, it makes a lot of sense. Now the optics will also have the capacity to walk around. Quite literally. So the microscope will run away from you. And
follow me.
Yeah. Okay, I think I'm gonna say goodbye to everybody online. Thanks so much for connecting. We have a lab session tomorrow. Please bring something. And then next week, Tuesday, is the deadline for the first assignment.
And
bye, everyone. Thanks, Benedict.
Bye.
Bye.